So we said that to get vector VA, or we can do it using the derivative of the position vector, or we can do it simply by saying we know that this angle between the horizontal and the vector is theta 2, vector position, and we know that the velocity is perpendicular to the radius, so we should add here 90 degrees, and this means that the angle between the velocity vector and the horizontal is theta 2 plus 90. So when I project, I get the magnitude, which is A omega 2, times cosine theta 2 plus 90, which is minus sine theta 2, plus the projection on J, which is sine 90 plus theta 2, which is equal to cosine theta 2. So both methods will give you the same expression for velocity of point A. Now, for P relative to A, same concept. Or you can use the method that you used here. And you say that if I take a frame translating at A and I look at P, P is rotating relative to A. So the velocity of P relative to A is perpendicular to vector AP. So VP relative to A will do with the horizontal a total angle of theta 3 plus delta 3 plus 90, okay? And the magnitude of this relative velocity is equal to the angular velocity of the coupler, which is omega 3, times the magnitude of AP, which we called small p, okay? That's why you will obtain exactly the same result of deriving the vector. Vector P relative to A is magnitude of the vector, which is P, times Ej theta 3 plus delta 3. When you derive, it's Jp omega 3 Ej theta 3 plus delta 3, or which is equivalent to P omega 3 times Ej 90 plus theta 3 plus delta 3, okay? So now, if you compare the two vectors, it's exactly the same. Along I, which is here the real part, you have P omega 3 minus sine theta 3 plus delta 3, while the complex part is equivalent to the projection along J vector, which is cosine theta 3 plus delta 3, okay? Now, the total velocity of point P will be simply the addition of VA plus VP relative to A. So you add the real parts together and the imaginary parts together, you will get the expression of the total velocity of any point of your coupler. You can do it for any point of interest for your coupler. All you need to know is the distance between A or B, and you can do the analysis also between points P and B. It's the same. Okay, so here we selected A. Then you have to know the distance between A and P and the relative angle here between AB and AP. And now we can do application of this. So as I told you, if they give you an application, you should make sure that the angles and vectors are defined in a similar way. And here, this is vector R2 because theta 2 is defined as this vector. This is vector R3. Okay, so this is similar to the way it's defined in the figure. This is R4. Okay, so the angle given is this one. If I change, let's say, theta 4. If theta 4, for example, for me is this one, I give you this angle. If I give you this angle, you say, in my expressions, I don't need this angle, I need this one. So if I give you, for example, alpha, you say, I need theta 4. So you do theta 4 is 180 minus alpha, okay? So because when you want to substitute in previous formulas, you need to make sure that all parameters are remaining the same, okay? So as we said, in this type of problems, we give lengths of all links. We give for a certain composition, the angle theta 2, the angular velocity of input link. We give for the coupler point P, the distance from A, and the relative angle between AB and AP. So all parameters are given. So just it's a substitution work, okay? So all we have to do is to say, I need first to do the position analysis to solve for theta 3, theta 4. Then I should do the velocity analysis to solve for omega 3, omega 4. And finally, they ask me to get velocity of point P. And since all of this work was already done, all I have to do is to replace in formulas. So you have these formulas developed in position analysis. And if you remember, for this configuration, we said we get two solutions for theta 3 and two solutions for theta 4. One corresponds, so these two will give me the open configuration, we'll see why, and these two will give me the crossed configuration. If you go back to your figure, if you remember in class we said that when we talk about open configuration, when we go from the coupler to the output link, we should move in the counterclockwise direction. Okay, so this angle corresponds to this one. It's equal to this one. Okay, so to move in counterclockwise direction from the coupler to the output link, we should calculate the angle theta 4 minus theta 3. In case we get a positive result, this means the angle is counterclockwise and this is open configuration. While if we get theta 4 minus theta 3 negative, this means that it's crossed configuration. So now if we go back to our solution, for the first case, when you do theta 4 minus theta 3, you get positive. So this is the open configuration. While for the second solution, when you do theta 4 minus theta 3, you get a negative result. So this corresponds to the crossed configuration. Okay. Now, second step, knowing now theta 3, theta 4, we can substitute into the expression of omega 3 and omega 4. So we can find angles omega 3 and omega angular velocities, omega 3 for the coupler and omega 4 for the output link. Now, keep in mind that you got two possible solutions. So you need to solve for the open configuration, what will be omega 3 and omega 4, and for the crossed configuration, what will be omega 3 and omega 4. So we'll get other values. Now, concerning the velocity of P, the velocity of the point P of the coupler, also we have developed the solution and we have all parameters. So we can solve for VP also for open configuration and for crossed configuration. Okay. Any question on this problem? Okay. Now, another type of problems, we have already also solved this problem in the case of position analysis, which is called slider crank system. So here it's all we have to do, as we said, is to detect the loop vector, the loop of vectors. Then we should ask ourselves which vectors have variable magnitude or variable angle. So let us start with the input link. So for the input link, it's adjoining two pivots. So it's of constant magnitude. You don't have any, if you want here, it's not a hydraulic cylinder, you don't have a slider. So this magnitude is fixed, but the angle is variable, okay? So we have here, for this vector, constant magnitude, variable angle. For the coupler, also, you are joining two pivots, A and B. So also, B is of constant magnitude, but this angle is varying because if you have a new position of your block, automatically this link, let's say, will change in angle, and this one also will change in angle. You have a new angular position, okay? However, if you take the third vector, if you remember the third vector, we got it from the projection of the block position on the horizontal that is coming from the origin, which is pivot O2, okay? And because of this configuration, it's clear that as the block is moving, this distance is not changing. This is called the offset distance in such systems. So since the offset distance is fixed, then this vector, which represents the projection vector It's perpendicular always to the horizontal. So this vector R4 will be constant in magnitude and constant in angle. So when you do the derivative to get the velocity equation, the derivative here will be 0. Now for vector R1, R1 will of course be variable in magnitude because as the block will move, you have a new projection and a new magnitude. But the angle will remain always 0 degrees because it's along the horizontal line. Okay, so now we know which vectors are varying in magnitude and which ones are varying in angles. Okay, you can have sometimes variation of both magnitude and angle. Okay, so now if I write the loop equation, so I have R2 minus R3 minus R4 minus R1 equal to 0. And I write the expressions of my vectors. For the first vector, the magnitude is A, the angle is theta 2. So in exponential form, I have A, E, J, theta 2. For the second one, the magnitude is B, the angle is theta 3. And since I want to do minus R3, so it's minus B, E, J, theta 3. Now, as we discussed, vector 4 has an angle of 90 degrees and a magnitude constant of C. So I can express it as minus CEJ 90. While for my vector R1, it doesn't have a vector along vertical, so it just have a real part in the exponential form. So I can write it as minus D equals to 0. And now to get the velocity equation, I derive. So as we said, for the first vector, magnitude is constant, angle is variable. So the derivative will be A times the derivative of the angle here, which is theta 2, and the derivative is omega 2. So A omega 2 EJ 90 plus theta 2. Or as you know, you can write it as, so you can remove 90 from here and multiply by J. Okay, this is equivalent because as we said, J is EJ 90. Okay, now we have that for this vector also, same thing, magnitude fixed, angle variable. So minus J times B times the derivative of the angle theta 3 with respect to time, which is omega 3, times EJ theta 3. We said that vector R4 is fixed in magnitude and in direction. So when I derive, it's 0. While for vector R1, it has only variation in magnitude. So when I derive, it's minus D dot equals to 0. And D dot actually represents the velocity of the block because look, when the block will move, so if the block will move, let's say a distance d prime, vector R1 will change with the same amount. So you can say that d represent actually the position of the block. Okay, so d prime will represent the velocity of the block. So d prime is just velocity of block B, the linear velocity of block B. Okay, so now this is our equation. After derivation, we got this relation. In this relation, the only unknowns are d dot and omega 3. So we need to identify the real part and the imaginary part to have two equations. So we know that the real part of this vector is minus A omega 2 sine theta 2. For this one, it's plus B omega 3 sine theta 3. And here, it has only a real part. So minus D dot equals to 0. While for the imaginary part, we have A omega 2 cosine theta 2 minus B omega 3 cosine theta 3. And for this one, no imaginary part. So we have two equations. Now, we can start from the second one because as you can see, in the second one, the only unknown is omega 3. So we can deduce from the second equation that omega 3 is A omega 2 cosine theta 2 over B cosine theta 3. Once we get omega 3, we substitute back in this equation, then the only unknown will be D dot, which is velocity of the block. So we can solve then for the linear velocity of the block. And now we are done with the velocity analysis. We expressed omega 3 B and VB. function of omega 2, theta 2, theta 3. Okay, so we are able now to solve for our velocity unknowns, angular and linear. This is a numerical example. Okay, in this case, we gave you the same vector configuration, so you can directly plug in the results. You have the length of your links. You have the offset distance, which represents this distance here. And as we said, the angle is constant and the distance is constant. So this is a constant vector. When we derive, it's equal to 0. And we have theta 2 and omega 2, which are the angular position and angular velocity of the input link. And they are asking us to solve for the velocity of A and the velocity of B. So to start with, we can directly find velocity of A because we know the distance from O2 to A, which is the length of link 2, 3 inch. And we know also the angular velocity of this link, which is minus 15 radian per second. So if you want, you have a negative angular velocity. If you are putting your velocity vector in this way, okay, and you put omega 2 times OA, you should pay attention that when you replace by algebraic value, which is minus 15. So automatically you know that the vector should be in opposite direction. So always these are algebraic values, and we developed relations based on omega 2. If omega 2 is positive, then the vector will be in this direction. While if omega 2 is negative, it will be in the opposite direction. Okay? So all you have to do is to replace into our developed equation before. So you can say, first, from my position analysis, I can solve for the value of theta 3. And also here I have two solutions. I have one for open configuration and one for closed configuration. And then for each configuration, I can solve for omega 3 and VB according to my developed relations now. I just substitute. I can get for open configuration what will be my velocities, omega 3 VB. And of course, before getting omega 3 VB, I should solve for the value of theta 3, okay, from the position analysis. Now, to get VA, I have two methods. The first one that we have seen in the figure, or I just say I need to derive vector position RA. So I have vector position RA, its derivative will be VA, which is A omega 2J EJ theta 2. Okay, now if I expand in Cartesian form or in exponential form, I get that the component in I is minus A omega 2 sine theta 2, and the component in J is A omega 2 cosine theta 2. So I can solve then for my velocity vector. I can do the calculation for open configuration, and I can do also the calculation for crossed configuration. Now, a last configuration is the inverted slider crank, which also we studied this configuration in the position analysis chapter. Just to remind you, in this case, you have the following. You have for your coupler, okay, on your coupler, this is your coupler, okay, so you have your coupler here. But what is happening is that for the output link is welded to a box. And this box is sliding relative to the coupler. So you can say here that because of this motion, okay, as the block is sliding, the length of this link will be variable. Because if I take, let's say, a new position, if the block is here now, okay, then your coupler length is from this point to this one. So this distance is changing. And because of this, okay, I need to, when I consider the position vector of the coupler, it will have two unknowns. It will have a magnitude that is unknown and also an angle theta 3 that is unknown, okay? So here vector AB, if you want, will be variable in magnitude and will be variable in direction. While if I consider, let's say, the input link, output link, for these two vectors, the magnitude is constant because it's joining, here it's joining two pivot points, and here it's joining the pivot to the block which is welded to it. So we have that this distance is constant. Okay, so for vectors R2 and R4, constant magnitude, varying angle. For vector AB, varying magnitude, varying angle. While for O2, O4, fixed magnitude, fixed angle. So when we derive, this vector will cancel out. So let us now write the loop equation for our slider system. So it's R2 minus R3 minus R4 minus R1 equals to 0. And we write the expression of each of our vectors. So we know that for the first vector, the magnitude is A, the angle is theta 2. For the second one, the angle is B, the magnitude is B, the angle is theta 3. And for the third one, the magnitude is C, the angle is theta 4. While for the final one, it does only have a real part. So it's just minus D equals to 0. Now we derive this relation, okay? And we said that this vector is constant in magnitude and in direction. So when I derive it, this term will cancel out. The most challenging derivation will be for this one, because for this one, you have variable magnitude and variable angle. So you will consider that B represent function U and theta 3 represent function V. And when you want to derive U times V, you do U prime V plus UV prime. So you first say the first term will be minus B dot EJ theta 3, then minus B times the derivative of this term. This is how you get the total derivative of this vector, okay? While for these two, A EJ theta 2 and C EJ theta 4, the only varying factor is the angle. So A, you don't need to derive A dot is 0. Okay.
دكتور
نعم.
بي دوت هون represents linear velocity تبع البلوك relative للكب.
Exactly. Yes. B dot represents the linear velocity of sliding of the block relative to the coupler. Exactly. Okay. So now, when we derive the relation, for the first vector, it's the conventional derivative, JA theta 2 omega 2. For the second vector, we divide the derivative into two parts, okay? So this is the derivative related to change in magnitude of B, and this is the component related to the change in angle. And because you have minus before the vector, so it's minus JB EJ theta 3 omega 3 minus B dot EJ theta 3. While for the third vector, as we said, only the angle is varying. So it's minus J C EJ theta 4 omega 4. And for O2 O4, it's a fixed vector. It will cancel out in derivation. Now, here, what are our unknowns? We have omega 3 as unknown. We have omega 4 as unknown. And also we have B dot as unknown. We have three unknowns, but keep in mind, what is the additional equations that we will add? And you will have two equations from the vectorial one or the exponential form one. And we have which relation you remember? We said here, because we have relative translation between the output and the coupler, the angle theta 4 minus theta 3 should be a constant. It's true that theta 3 can vary and theta 4 can vary, but the difference between them should remain constant because they cannot rotate relative to each other. They only have relative translation with respect to each other. So since theta 4 minus theta 3 is a constant, so when I derive this relation, I get that theta dot 4 minus theta dot 3 is 0. This means that the angular velocity of link 3 is equal to the angular velocity of link 4. And this is expected because they should rotate at same angular velocity to keep same angle between them. Okay, so now I have 3 equations, 3 unknowns. So I can substitute, if you want, here, I can substitute omega 4 by omega 3 because they are equal. And then the vectorial or exponential equation will give me 2 equations, 2 unknowns. The real part will give me the first equation, and the imaginary part will give me the second equation. Now, as we mentioned, to do the analysis of the terms, the first derivative will give me the velocity of point A, okay? Here, we have 2 components. So as Mario asked, we have one component for slipping, for relative slipping between the block and the coupler. So this represents the slipping velocity, and this represents the rotation of B around A. So in total, if you want, this is VB relative to A that is decomposed into 2 parts, which is the rotation of A around the B, the relative rotation between A and B, and the slip due to translation, okay? And this term is VB, okay? So in total, when you add the 3 terms, you will get this is equal to 0, okay? Here, if you identify the real part and imaginary part, you get your 2 equations, and you can see that you have coupled equations. So you can substitute, for example, you can get omega 4 function of B dot, then replace in this equation. So you can solve for omega 4 expression and B dot expression, okay? Any question on this? So here, if you want, when we talk about VAB, okay, you know that this vector, okay, if you go back to the figure, this vector AB, when you derive AB, okay, you get VB relative to A. But since we considered, if you look at the analysis, the vector considered is not AB, it's BA. It's from B to A, okay? That's why when you derive, okay, when you derive this expression, you will get VA, VB, okay, because we put minus, we are considering the opposite vector, okay? So you will get then minus, if you want, so it's or, you can consider it as or VB relative to A, okay, or minus VA relative to B. So because VB relative to A is equal to minus VA relative to B, okay? So this is why we have the minus, because we considered the opposite vector, okay? So when you put the minus again, you will go back to vector VB relative to A. And when you add VA, this will give you VB. And of course, if you do VB minus VB, you will get 0. Okay, so this equation will give you 0 because you are getting from the 2 terms, from the first 2 terms, you get VB. And then you do minus VB, so you will get 0. Okay, and to identify, to understand the physical meaning of your terms, you have one term that will give you the rotational component and one term that will give you the slipping component, okay? And then you have to solve for your 2 unknowns, which are B dot and omega 4, because omega 3 and omega 4 are equal, okay? So this is the problem of a slider, now inverted slider system. And now, as we mentioned, the slip velocity is B dot, okay? It represents the slipping of the block on the coupler. If you want to solve for the velocity of point A, it's simply the derivative of position vector. So it's GA omega 2 EJ theta 2. If you want to solve for velocity of point B, then you say what point B is given by vector O4 B, okay? And this vector has a magnitude of C, and has an angle with the horizontal equal to theta 4. So I can define vector VB4 as GC omega 4 EJ theta 4, which is equivalent to C omega 4 minus sine theta 4 plus J cosine theta 4. Okay, and since you have that, if you are interested now to get to understand how to get B in another way, so you can get VB as a point of the output link, but also B is a point on your coupler. And from your coupler analysis, point B velocity is affected by two things. You have the rotational component and you have the slipping component. That's why, so these are the two terms that we identified in the previous relation. Okay, so you have to do, you are taking the same point B, but here you are considering it first as a point. One time you considered it as a point of the output link, and one time you considered it as a point of your coupler. Okay, so you can say that the velocity of B can be written in another way. It's equal to the rotational velocity plus the slipping velocity. Okay, so in this way, when you related the loop, you got VB minus VB equal to 0. And since you got VB in two different ways, you were able to solve for your unknowns. You got a relation including your unknowns. Okay. And this is an example on an inverted slider crank. So here you have exactly the vectors are defined in the same way as given in the figure. So I repeat, in order to use the same formulas, you should stick to the same parameters. So in case I vary anything in the figure, you should go back to give the parameters needed to plug in your equations. So here, since I gave same angle, same configuration, so I just plug in directly. I have the length of my links. I have the difference between my angles. So I know what is the difference between theta 3 and theta 4. It's provided. I know the input angle and the angular velocity of my input link. And they are asking me to solve for velocity of A, velocity of B, and slipping velocity. So here, it's just an application. I say I already developed all equations. I start, of course, by position analysis to solve for theta 3, theta 4, because I need them to plug them into the equations in velocity to get my unknowns of velocity. My velocity unknowns will be B dot, which is the slipping velocity, and omega dot theta dot 3, which is equal to theta dot 4. So omega 3 or omega 4 will be the same. Okay, so all I have to do is just to go back to the formulas developed in position analysis in order to solve for my angles, theta 3, theta 4, and also for the length of my coupler B. Here also I have two configuration, open and crossed, so I can solve for values in open and values in crossed configuration. Then once I get my vectors, I can calculate according to the formulas developed omega 3 and beta dot. And this will give me the velocity unknowns. Then because I asked to find the velocity of A, the velocity of point B, and the slip velocity, I can use the formulas developed. So V slip is just B dot. And if I want the vector, I just have to consider, so I know that my vector is of magnitude B dot, and the angle it's doing with the horizontal is given by, if I go to my figure, okay, the slip velocity is along this direction. Okay, so if I need this angle with the positive x-axis, if I look at my figure, this corresponds to theta 3 minus 180. Why? Because please remember that they defined the vector position, they defined it from B to A. Okay, while the slipping velocity, when I got B dot positive, this means that the slipping velocity is from A to B. So if I need this angle of the slipping velocity, I should do theta 3 minus 180 to get this angle. Okay, and then I still need to find the velocity of A and B, it's very simple. Once I have omega 2, omega 4, and I know the magnitudes of the links, I can get VB. You can verify that you can VB, you can get VB by another way, which is by decomposing VB into VA plus velocity of B relative to A. And we mentioned that the velocity of B relative to A is divided into two components, slipping component and rotational component. So we can find VB by two ways from doing the analysis of the first part of the mechanism. Yani we do the analysis from O2 to B because we find VA and then we calculate the velocity of B relative to A, or we can directly say B is a point of the output link. So we find VB from the output link. And when you write your loop at the end and you derive, you will get VB minus VB equal to 0. But because you got them in two different ways, you get your equations that will allow you to solve for omega 3 and B dot. Okay, so that's it. In this way, you can solve for all of your unknowns. Any questions on this?
دكتور
Okay.
هتنزل ريكورد هلا ولا امتى؟
Yes, I will upload the record, of course. Here in the last slide, they are just telling you that you can use the analytical method or exponential or real imaginary method to give you vectors. Okay, so you can use the method that you feel comfortable with. The two methods are right. You can write in exponential form, or you can divide your vector into ij components and then derive the component along I. You get the vector in I, and derive component, let's say, along j. So if you want f dot, you have just to derive component along I to get f dot in I, and derive component along j to get f dot in j. But the imaginary complex, the complex numbers form is also applicable. And both methods will give you exactly the same result. Okay. I will post these recordings, of course, and I will send you a link to watch them. Any question before we stop? Okay, thank you, guys.
Thank you, Doctor.
Bye bye.
دكتور
Yes?
صلحتي الاكزامز؟
Yes, but I didn't finish. When I'm done, next week, Akid, I will bring them, okay, to university.
Thank you.
Bye bye.
Bye.